Chapter 9, Section 2. Inferences about two proportions. By the way, this word we've actually been studying for some time now. It's a branch of statistics called inferential statistics. Do you guys know the word inference? To guess? That's, yeah. Educated guess maybe is better than that. Yeah. Somehow, we want to say something we don't know the answer to, but we're going to use some sound scientific method, in this case statistical method, to do it. Inferential statistics is saying something about a population based on data from what? Samples. And I'll put samples. Right? We had been using one sample and one population. Now we're going to have, more than one population we want to talk about. This whole section is how do we do that, this whole chapter? Okay, guys, so what are we doing in this section? Well, these are long slides, so let me just highlight the main words here. Number 1, testing a claim about two population proportions. And then number 2, oh, look at this thing. Remember the word confidence interval? We're going to construct a confidence interval. Confidence interval for what? The difference between two population proportions. Yeah, that's a key idea. Is that usually what you want to study is the difference between two population proportions. So you'll see that coming up as I go through the slides here. Now, when your book starts out this section, there's a yellow, a big yellow kind of rectangle that says notation, because, there's a lot of notation that you wouldn't have been ready for a couple weeks ago, but you are now. Yeah, check this out. Page 462 and 463, you'll find all this. You don't need to write this all down. But I thought before I start, I could at least show it to you. Okay? P1, what's P stand for? The proportion. And that says population. What are we going to do if it's a sample proportion? Put a hat above it. Right? Put a hat above it. N1 is the size of the sample. Which sample? Sample number 1. We're just going to put little ones, kind of like I did on the board before, if we're talking about population 1. X1 is the number of successes. So when we talk about the proportion, we've seen this before, P hat is X over N. Right? Well, now I'll put a bunch of 1s there if I'm talking about number 1. I'll put a bunch of 2s there if I'm talking about number 2. How you doing, Noah? Good. And then Q hat, right? 1 minus P hat. We've seen that before. Okay. Now this is new. This one you probably do want to write down. The pooled sample proportion going to denote that by P bar. Okay. And it's given by this. No. So let's see. I'm trying to think about our little example up front where we had the pulse rates. Remember the pulse rates? What would N1 and N2 be for the pulse rates? 7, right? So maybe we might be thinking about, I don't know, the proportion of pulse rates above, I don't know, 80. We might be thinking about that. Well, in our sample of males, P1 was something out of 7, and P2 for females, oh, by the way, these should have hats above them because these are based on our samples. We don't know the population proportion. P2 hat was also something out of 7. What do we get? Looks like for the males we had 2 out of 7. Right? How about for the females? How many were above 80? Oh, yeah. So that's a good question. Do I include the 80? I said above, so I guess not, huh? I guess that'd also be 2 out of 7. If I say greater than or equal to 80, then this would be 3 out of 7, right? Okay. It depends how you do it. But then, what would P bar be for this example? 5 out of 14, okay? This is what you call the pooled sample proportion. We're going to see that comes up. That's something we need to know. Right? You're pooling the two samples together. That's why they use that language. Okay? Now, we denote the complement of P bar by Q bar. So Q bar is 1 minus P bar. All right, tell me guys, in our example, what would Q bar equal? 9/14. Right? Because 9/14 plus 5/14 has to equal 1. That's the idea. So actually, I think the notation they use is pretty easy to follow for you guys. With as much as you've done with this stuff already, it's not that bad. Requirements. Oh yeah, we always have requirements when we want to perform certain tests. So we're going to test these we're going to do some statistics to say something about the population proportion. Hey, you guys want to guess what some of the requirements are? Simple random sample. What else? Well, that's what you call a standard normal distribution. We're not going to need that here. Well, here, I'll put them out. We don't have to guess. First requirement. Oh, here's a new word. We have to have proportions from two independent. Now, you're right, simple random samples. But we have to talk about what it means for them to be independent. Now, I used that word earlier in this course, didn't I? Yeah. It's going to have a similar meaning, but not exactly the same. So I'll talk about it. Also, for each of the two samples, the number of successes is at least 5, and the number of failures is at least 5. Yeah, so you can throw my example out the window when you guys said you only have 7 of each data, right? Well, okay. That's not enough. We have to have enough that whatever you're talking about success-wise, you have at least 5. Otherwise, the data is not going to be distributed the way we want it. It's not good enough, that's right. If you had 5 out of 14 and 6 out of 14, then you could probably say something, yeah. Now let's see what else we have. What's that? Oh, because what you call success and failure is very arbitrary, right? So if I said, okay, let me go back to my example. The proportion of pulse rates greater than or equal to 80. Oh, that's not good enough. Oh, I know what I'll do. I'll do the proportion of pulse rates less than 80. 5 out of 7, I'm in good shape. Well, if you're not in good shape for the one, you're not in good shape for the other. Okay? So it has nothing to do with what you call success and failure. The point is that we want to have at least 5 of each. Not for these methods to work. Usually you'll have quite a bit more than that. We've mentioned the number 30 before, okay, for the size of a sample when you want to start approximating a normal distribution.
So if it was something and you had like maybe 10 pulses, 5 have to be at that point, 5 has to be, like if you want like over 85 have to be,
Yeah.
has to be over 80.
Right. Right. Okay. I haven't been a real stickler for the requirements. The main point I want you to know is that every test has certain requirements, right? And you have to check that you have those before you start. But in terms of memorizing what they all are for each kind of test we do, that's not worth it. You should look them up when you're doing a test. Okay. Test statistic for 2 proportions. If we have 2 proportions and we want to test a claim, you guys know by now that you have something called a test statistic that you can compute. What do you do with the test statistic, by the way? That's how you get your p-value, right? You take the test statistic and you can get the probability of being at least that extreme. That's called the p-value. Then if p is low, null must go, right? Or what's the other thing you could do with this test statistic if you wanted? Yeah, you could put it on the graph and see if it's and it can give you see if it's in the critical region. That's right. Now you mentioned margin of error. When do we compute margin of error? That's if we're trying to construct what? Confidence intervals. We're going to do that today too. Okay, that's the second thing I'm going to do. Now, oh boy, this is just a mess. It's a big, ugly test statistic. Well, okay, first of all, what are we testing? We're testing things like P1. Well, we're trying to reject the null hypothesis that P1 equals P2. Maybe the claim is P1 does not equal P2. By the way, what's the difference between that and one of these over here? Two-tailed, one-tailed, one-tailed, right? Left-tailed and right-tailed. So all this kind of stuff you've seen before. The only difference was you didn't have P2 over here. What did you have over here? Some number. Now you actually have P1 and P2. And if you notice what's happening here, it's almost like this. Let's see if this makes sense to you guys. Let's let P equal P1 minus P2 for a minute. And let's let P hat equal, what do you think I'm going to say? P1 hat minus P2 hat, okay? Now, P and P hat, I just made those up. You might say, why did I do that? Well, here's why. Because then the numerator is just P hat minus P. Isn't that the test statistic we used in Chapter 8 when we were doing proportions? It was P hat minus P. Do you remember what the denominator was? Wasn't it PQ over N in the square root? Wasn't that it? That's what you did. Now, it turns out that if you do this, that almost works down here. This isn't quite PQ over N. It's a little different. I guess I'm trying to show you why this complicated formula is believable as the right thing to do. Because, yeah, if you put in P and P hat, you'd basically be back to what we did in Chapter 8. The only difference is, what about this stuff down here? And by the way, wasn't this hat down here? Yeah, these were hats. Oh, they were P and Q? Okay. I thought we had hats. Okay. It turns out that what we're going to use as an estimate of the... See, basically that's the variance down there for a proportion. It turns out that you need to use P bar and Q bar. And what does that bar represent again? What's this thing called? That's the pooled proportion. So again, that's that thing I went over, well, 2 slides ago. Right? This P bar is going to be an important thing to compute. So as we do an example, we'll go ahead and do that. Okay. Let's see. Oh, I don't want to do that yet. Hold on. Yeah, I do. The second thing we will do is we will do confidence intervals. What do confidence intervals look like? Well, they look like this, right? And again, this is what I call P, right? P1 minus P2. We want to compute. We want to talk about the difference in the population proportions. Maybe they're different. And again, this is P hat minus E, right? And what's this? P hat plus E. So does this look any different than what you had before? Not really, right? The only thing that's different is that instead of P hat, you have a difference. Instead of P, you have a difference. That's the thing. You open up Chapter 9, and the formulas are huge. But because you've done Chapter 8, you're saying, oh, I get it. I've done this before. It's just more complicated now. There's a difference there. Now, in the old days, we computed E, the margin of error. How do we do it? Did we have Z alpha over 2 in the old days? We sure did, right? We got the margin of error using Z alpha over 2 when we were talking about proportions. What did we use when we were talking about means? Do you remember what went here instead? The T distribution, right? So that's going to come back, by the way, in the next section. And now what do we have here? What did we have in Chapter 8 when we were doing margin of error? Didn't we just have one of these? It was just the square root of P hat Q hat over N. Well, here's the deal. The variance of P1 hat minus P2 hat is the variance of P1 plus the variance of P2. It's kind of weird. You could prove this mathematically, and in this course we don't do that. But I'm just telling you that when you compute variances of a difference, you actually have to add the variances together. Think of it this way. What does variance tell you? Oh, well then if we don't have that, then I'm not succeeding. Well, it's standard deviation squared. Okay, so let me ask this. What does standard deviation tell you? If what? Yeah, that's one way we used it, right? How far away you are from the mean. That's right. Now here's the idea behind this. I have a proportion. Say I tell you the standard deviation is 100. That means on the average, how far is that away from the, how far is the data away from that proportion? Maybe 100. Okay? And then I have another proportion, and maybe it's 100 away. Well, when I subtract those proportions, how far away could the two data points be from the difference? The answer is you could be up to 200 away, because if you're 100 one way from one and 100 the other way from the other, those are 200 apart when you subtract. Okay, people are shutting the eyes. Too much math. I'm done. Back to stats. This one down here? Forget it. I'm done with it. It's never coming back. All that's doing is explaining why there's a plus sign here. That's all that's doing. Not needed to know for this class. But sometimes, you know, you get this formula and you're like, why? Where'd that come from? I guess it is important to know, though, even though this is subtract, this is add. Okay? So keep that in mind. You don't want to put a minus sign there, you'd be in trouble. Okay, example from the book. Let me pause and find what page. When it says use a 0.05 significance level, what does that mean? What's 0.05? Okay, we call that alpha. I'll write that down. We want to test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags. The fatality rate. By the way, it says lower for those in cars equipped with airbags. So here I have airbags, right? And here I don't. I guess what I could do is I could compute the fatality rate, right? How would I do that? Yeah, that's all there is to it. Sorry about this. Give me 1 second here. I want to get my calculator back so I can actually... Oh, boy. Action. As I said, we have a calculator. That's fantastic. So we can compute the fatality rate from example 1. How do you compute the fatality rate? 41 fatalities. 11, 5, 4, 1. By the way, this is what I mean by a proportion, right? That's my x1 over n1. Okay? So I'm going to say, oh boy, luckily there's not that many fatalities, right? At least the rate isn't that high. It's 3.5 of a percent. 0.0035. Okay, that's my P1 hat, if you want. Because again, this is a sample. A simple random sample, it says. Okay? And I could also compute P2 hat. Now, I don't have as big a sample for those with no airbags. But that's okay. 52 divided by 9853 is enough to give me a proportion. Okay. 0.00528. Okay? So there's P1 hat and P2 hat. What's the claim? Yeah. Almost. Claim is that P1 is less than P2. See that? P1 is less than P2. That's the claim. It could be H1, right? Because what would the null hypothesis H0 be? P1 is equal to P2. So yeah, you could make this H1 if you want. Okay. Requirements, there's, oh yeah, they'll say, we should check our requirements. Are they satisfied? So they say, hey guys, we have 2 simple random samples. They're independent. We have at least 5 successes and 5 failures, right? Tons of them, actually. Use the p-value method. Okay. So they did all this stuff with the claims. We just did that. I'm going to move on. We talked about alpha. Okay, step 5. Use the normal distribution as an approximation. Okay, fine. Here is something you need to compute. P bar, what's that called? The pooled. I'm not going to have you write this all out. It's in your book on page 464. They do this. But yeah, that's a computation they made. Once you have P bar, how do you get Q bar? To subtract 1 minus P bar, right? Okay. And why are we computing the pooled proportions? Well, because those are going to show up in the test statistic. So if I go to the next, either down a few lines in your book or my next slide, here's the test statistic, and that's where the P bar and Q bar show up, is in the denominator. Now you notice something here. Why did they put a 0 here? What was supposed to be there? P1 minus P2. Well, we don't know P1 and P2, but we're making a claim, right? The claim was what? P1 is less than P2. That was my H1, it turns out. And then H0 was what? P1 equals P2. Okay, now, just so you understand this, if P1 equals P2, what would be P1 minus P2? That's the same as P1 minus P2 equaling 0. You get that? So we are computing a test statistic. I guess the point is we are testing which claim? H0. We're testing the null hypothesis. Does that make sense to people? And if we get a really low p-value, we're going to say, oh, H0 is wrong. So that's the idea. Well, they did this whole computation, and they did it for us. I'm not doing it on our calculator. They get the z value is negative 1.91. So now what do you do? Well, is this a one-tailed test or a two-tailed test? Left-tailed, right? Because here it is. P1 is less than P2, right? So what I'm going to do is draw a picture, and I'm going to put my negative 1.91 where it belongs. So let's see, here's 0, here's 1. So right over here somewhere is negative 1.91. And basically, this area is the p-value. Capital P. So how do I get that area? Well, for using the calculator, it's normal CDF to get areas. Say from negative, whatever you want, 12 to negative 1.91, or negative 10 to negative 1.91. Anything like that will work. And let's see. May as well do it. So I'll hit second variables, or second, that gives me distribution. Normal CDF, negative 10, comma, negative 1.91. And I got an area of 2.8%. Annette, Amber, you guys with me? No. Okay. Question. Let me point that out. I did negative 10 in the calculator. If you do negative 12, it's going to get you the same thing. Because by the time you're that far out, it's almost on the x-axis. It's just above. So you get basically no more area. Yeah, that was just kind of, I typed it by accident. But the point is you want to be way out left and come up to negative 1.91. So this area, what do we get that it is? This area is 0.028 in there, and that's my capital P value. 0.028. By the way, is that low? Because what was our alpha? Yeah, so that's low. So what's that mean? Null must go. And if you read the rest of the example, right, they did this. There's the picture. Yeah, we reject the null hypothesis. Now, here's the hard part for a lot of you guys is now, how do you put this into English? We reject the null hypothesis, and here it is in English. We conclude there is sufficient evidence to support the claim. Which claim? What? The original claim. And what was that claim? The proportion of accident fatalities for occupants in cars with airbags is less than the proportion of fatalities with occupants in cars without airbags. Based on these results, it appears that airbags are effective in saving lives. So I'll tell you what, you get a study like that, guess what happens? The law changes, right? Manufacturers, after studies like this, start putting airbags in cars. Does that make sense to you? Okay. It's based on statistical studies like this. Cool. Yeah, this is exactly what you're going to do on your homework. By the way, we also learned, remember, about the traditional method. In the traditional method, here's what you do. You take your alpha, you put it on the left in a picture, and you compute this z-score. This z-score is called the, do you remember? Critical value. Let me show you how to get the critical value. As a reminder, what do? Yeah, that's where you want to do inverse normal distribution. Inverse norm of 0.05, and that should give me the negative, some of you guys have that one memorized, negative 1.645. We've had that a few times, right? The 1.96 one's the one you usually remember, because that's when you have a two-tailed test, what you get. And then, I'm going to get your question in a sec, right? Because the test statistic ended up in the red in the critical value, that would also tell you we're going to reject the null hypothesis. Okay, Craig, your question? Yeah, and that's when you get the negative 1.96 and positive 1.96 for the critical values. So it is very important if it's a one-tailed test or a two-tailed test.
So is there a rule when you use normal CDF that inverse norm?
Yeah. Normal CDF is what you use if you're trying to get the area or trying to get the probability. What does inverse norm give you?
Oh, that gives you the probability.
Inverse norm gives you z values. And for those of you that are using the table in the back of the book, it's going forwards or backwards, right? So, same idea. Caution. Okay. The p-value method and the traditional method, they're both fine. They're the same. They're equivalent. But these are not equivalent to confidence intervals. Confidence intervals may give you a different result. Yep. Yep. So, as an example, this is where they're going to do a confidence interval in the book. Let's find that. Example 2. They're going to do a confidence interval for airbags. It says, let's use that data to construct a 90% confidence interval estimate of the difference. So what's that mean? That means we're going to get, the difference between P1 and P2 and bound it. Now, it's kind of funny. Because I think P1 is smaller than P2, I wonder if they're going to do this in the book. I might do that. P2 minus P1, Because P2 is bigger. But we'll see what they do here. They do P1 minus P2 and they don't worry about it. Okay. They check that the requirements are the same, yes. 90% confidence interval. That means alpha equals what? 0.10. Look what they got for z alpha over 2. Does that number look familiar? Yeah, why is that z alpha over 2? Because, well, it's z of 0.05, which is what we just computed. Right? So that number goes in front. Z alpha over 2 is in front of the big square root. Everything else, do you guys know what those letters stand for? You could fill them in like the book did if you had to. Take a look. Okay, moving on. You want to construct the confidence interval. For what? For the difference, P1 minus P2. Yeah, see what they did? Because they did P1 minus P2 in the book, look what happened. Both these numbers are negative. Well, we knew it had to be negative because we just said that P2 is bigger than P1, right? What does E stand for? Margin of error. Now, these are the proportions that we computed from the samples. And the E is what we just computed that had that Z alpha over 2 in the front. Anyways, here's my 90% confidence interval. So you know what that means? I'm 90% sure that the difference between these two proportions is not very big. Right? I mean, that's not a big number. It's less than 1%. This is all in the book. But here is the important fact about your confidence interval. The confidence interval limits do not contain 0. Ooh, that's important. Because that implies there is a difference. The difference is positive. That's what we're implying. Now, are we certain that the difference is positive? No, we're not certain. Take a look at those numbers again, right? I mean, maybe the difference is only this much. And you could use a higher confidence interval, but if you do, what's going to happen if you make alpha bigger, if you make alpha smaller and are more confident, then the confidence interval gets bigger, right? And so then you might contain 0. And if you contain 0, the proportions could be the same. wonder if it would contain 0. I didn't do the calculation, and the book didn't either. That's a good question. Okay, so I left space here to do a problem if we want to do one out of the book. But part of me thinks it might be time to move on to means.